Hello everyone, this is an introductory session to aerodynamics. This will be beneficial to all the club members who wants to study the more advanced stuff of aerodynamics in future. So this will build the fundamentals of it. So let's start today's session, and this will be the flow of lecture today. First, we will start with basic terminologies related to aerodynamics. Next, we will talk about important principles and their application. After that, we will discuss about the objectives which we need for our Formula student vehicle. After that, we will discuss about certain parameters which would help us achieve those objectives. Next, we will talk about some simulations and testing and the design validation process in general. And after that, we will conclude the lecture and have some final thoughts. Okay, so let's start. Okay, so before the study of aerodynamics, we must be able to tell what the term actually means, what this is aerodynamic actually means. So as you might know that this is actually made up of two separate words. So this is aero and dynamics. So what does this aero signifies? Aero signifies that the working fluid which we are talking about here is air. If the working fluid would have been water, we would call it hydrodynamics. The hydro would be added here, and dynamics means the study of motion. Okay, one very certain thing which many miss is that can you tell me the difference between dynamics and kinematics? So this is a very interesting question about how these two things are different. Both are study of motions. So the basic difference is that in dynamics we talk about the forces involved in the motion, right? We talk about the forces which are involved. While in kinematics we do not talk about the forces. Instead, we talk of other parameters such as displacement, velocity, and acceleration. Okay, so coming to the next thing, if you are studying the fluid properties, one thing you should actually be able to differentiate is what is the fluid. What does fluid mean in general? So the definition of fluid says that any fluid should have a flowing characteristic. That means even with a very little force, it has a high deformation. That is, even with very little stress induced, the deformation, the strain produced is very high. Flows, it continuously flows around, even if very little force is there. So the flowing characteristics defines the fluid. Okay, one other thing which we need to know is what is an ideal fluid and how it's different from a real fluid. So ideal fluid takes the consideration that the fluid which we are dealing with is neither viscous nor compressible. So it is inviscid and incompressible. These two conditions are generally true. First, let me tell you what are these two things. Inviscous means that the viscous effect of the fluid is negligible. We neglect the viscous forces, and incompressible means that the density throughout the flow region remains constant. Okay, so these two terms are generally valid for almost all flow. For inviscous, if we talk about the air stream which is at a distance from the surface, so very little, very close to the surface, there is a layer called the boundary layer, and in that layer only the viscous forces are prominent. In the free stream condition, that is the air stream which is not affected by the object, there this viscous effect is not very prominent. And also the compressible terms which we have talked about depends upon the speed of the speed of the flow. If the flow speed is very high, by saying that the flow speed is high, I mean the flow is high with respect to its acoustic velocity. So this ratio, the velocity of flow to the acoustic velocity, this is called as a Mach number. So if Mach number is high, generally taking 0.5, if that is the case, then we have to consider the compressible effect, otherwise we neglect it. Okay, so that's an ideal fluid. Okay, so anytime the airstream is obstructed by an object, the air particles collides with the object and imparts momentum to it, and that imparted momentum creates a reaction force. Right, this is reaction force is created, and if we resolve this reaction force into two components, we get the drag and the lift force. The component of reaction force which is along the airstream, this is called as a drag force, and the component of reaction force which is perpendicular to the airstream, this is the airstream and this is perpendicular to it, so this is called as a lift force. Okay, so this is valid for any geometrical figure which obstruct the airflow have these components of forces which are the reaction force. reaction force, these two components are present there. But one thing to note is that the drag component is very high as compared to the lift force. Lift is very little and it is not very much, not very substantial actually. So it would be enough for a sustained flight, and this thing would eventually fall under its own weight. Okay. Next thing which we talk about is that if we obstruct the airstream head on, if this thing is 90 degrees to the airstream, this is completely blocking the airstream, and this creates the reaction force uh, is converted wholly into drag, and we do not get any lifting component out of it. So please note that the drag force exists even if lift exists or not. So anytime you put an obstruction, you are bound to get the drag force. You might want to minimize it, but you cannot completely eliminate it. Okay, before proceeding, let us talk a little about wing geometry. So this is the standard wing design taken from NPTEL lecture. So uh, this is a basic configuration of a wing design. So there are some certain geometry which we need to discuss. So if this wing that is attaching to the fuselage, so this is the center of the fuselage, center line of the fuselage, the wing where it joins to the center line, this total distance from here to here, this distance from here to here, this distance is called as the root chord, and at the tip it tapers down at the tip. So at the tip the length, this is called as the tip chord, this is the root chord, this is the tip chord. Okay, and the total distance from one tip of the wing to the other tip, this length is called as the span of the wing. Span of the wing, very important. And how of it's called semi-span. S is the area, this hatched section, this is the area, capital S, this hatched section, wing reference area, or it's also called the plane form area. Okay, so wing has a very certain, very distinct geometry. So if we cut the wing along one section and see it through, we will get this type of shape. This shape is called aerofoil shape, and this aerofoil shape is responsible for creating lift just because of its geometry. The geometry is such that this creates lift. We will see that later. So this is an airfoil, and this is the top surface of the airfoil. This is the bottom surface of the airfoil. Also, this is called as the leading edge of the wing, and this is called as the trailing edge of the wing. So this point is in the leading edge and this point is in the trailing edge. We are seeing the cross section view of this. So if we join the leading edge to the trailing edge with a straight line, this straight line is called as the chord of the wing or chord of the airfoil. The maximum distance which is between the upper surface and the lower surface is called as the thickness of the wing, and the angle with which the airfoil attacks or encounters the incoming airstream. Here the incoming airstream is like this, and this is how the airfoil is interacting with it. This angle is the chord line makes with the airstream. This angle is called as the angle of attack, alpha. Okay, so taper ratio, as you see the wing is getting tapered down, so Ct upon Co, tip chord by root chord, this is called as the taper ratio. Another very important parameter is called as the aspect ratio. This aspect ratio is the span square upon area, plane form area. So this b square upon this area, this is an aspect ratio. Aspect ratio represents the slenderness or length of the wing. So if a wing has a greater aspect ratio, this span would be higher for same area. Okay, this is t by c, this is called as a thickness ratio. So this is a general airfoil design which we seen in the previous slide also. As you see, this is the leading edge, this is the trailing edge, straight line connecting these two. This is called as the chord line, and see, this is an unsymmetrical airfoil, right? This is an unsymmetrical airfoil. So chord line does not bisects the two region into equal parts. So that we do with an imaginary line. So this imaginary line right here, this divides the section into two equal halves, and this line is called as the mean camber line. And the distance between the mean camber line to the chord line, this length is called as the camber of the airfoil. More the camber, more is the curvature of the airfoil. So camber represents the airfoil curvature, right? Hmm. So, airfoil is a well-crafted geometrical shape which is used to which is used to maximize lift and minimize drag. So, how does this do so? So, this creates a very special type of streamline flow around it. So, this is the airflow streamline. So, what does the streamline mean? Streamline means that it shows the motion of the particle. If at any point of a streamline you took a tangent to it, that tangent would give you the velocity of the air particle. So that is a streamline. So because of the shape of the airfoil, it creates a low pressure region here and a high pressure region at the bottom. Low pressure region at top and high pressure region at the bottom. And this difference in pressure creates a lift force. This is a resultant lift force, and it occurs at the quad upon fourth, quarter chord length. So there is the resultant lift which occurs. This is because of the geometry. There creates a low pressure region and high pressure region, and this pressure differential creates a lift. So I have a question for you. Can you tell me why this low pressure and high pressure region are created? What is the basic reason of it? So think about it for a second, and we will answer that in the next part.